So now that we've talked about what the graphs of multivariable functions, specifically two variable functions look like, we should talk about how to do calculus with them. So since we're dealing with functions of multiple variables, the notation for the derivative doesn't quite make sense anymore. This Newton's notation, just f prime, doesn't quite make sense anymore because it doesn't tell us like which variable we're really looking at. So remember, the other notation for f prime was Leibniz notation, which was d dx. And then we would say we're differentiating with respect to x. This variable on the bottom, we would say differentiating with respect to. Now, sometimes it wasn't that necessary. If we were just saying f prime, then there was really no problem. We could just keep, we didn't have to like specify which variable we're differentiating looking at because there was only one variable. But when we start dealing with multiple variables, we really have to make it clear what variable am I focused on right now. And so to do that, we'll use this special notation. We actually use a fancy, instead of this just regular d dx, we use this fancy cursive guy. So this is the partial derivative with respect to x, or we can just say f sub x, or we could say, the partial with respect to y, or you can make it clear what function you're differentiating, so df dy, partial f, partial y. And this just makes it clear that there are other variables that I could have chosen, but I chose y in this case. And then the nice thing is for you, once you choose your variable, you treat everything else as a constant. So remember, in single variable calculus, when you're differentiating constants, they just differentiate to 0. So in this case, if you're differentiating with respect to x, for example, and you differentiate, I don't know, a y or any other variable, it just differentiates to 0, just like you would differentiate some constant, like a 5. So let's see this in action. Here's a two-variable function, 2x cubed y squared plus 2y plus 4x. Now I'm going to find two derivatives. First, I'm going to find the partial derivative of f with respect to x, and I can see just reading this notation, clearly there were other variables for me to choose because we use this fancy cursive df dx. And then I'm also going to find the partial derivative of f with respect to y. So, let's see, let's start with finding the partial with respect to x of x, y. Now, when we're differentiating with respect to x, everything that is not x, so this 2y squared, is treated as a constant. I'm just going to pull that out to the front. And then I'm going to differentiate the x cubed portion of this like I normally would. So this differentiates to 3x squared. Notice that we didn't use product rule here because really there is only one variable that I see in this expression when I'm doing a partial derivative. I don't even see y squared as a variable or y as a variable. So also here, I don't see this 2y as a variable. I see it as a constant, so that differentiates to 0. And then for the third term, 4x, well, we just differentiate like normal, and that differentiates to 4. So when I simplify this whole thing, I get 6x squared y squared plus 4 as my partial with respect to x. And if I wanted to plug in a point here, now plug in values for x and y, I could do that also, or I can just find a function that represents the partial derivative. So now let's do the same thing, except let's differentiate f with respect to y. So df dy partial f with respect to y. Now, when I'm differentiating with respect to y, this entire portion of my first term is just a constant. So I'm going to bring that to the front and not do anything with it. And no need for product rule because there's only one variable that I see, which is only this y squared, and I differentiate like normal. So that differentiates to 2y. And then I differentiate my second term like normal. So 2y differentiates to 2, and then 4x, well, I don't see any variables there because I'm only looking for y's, so that last term differentiates to 0. And when I simplify this whole thing, I get 4x cubed y plus 2. And again, this is just a function right now, another two-variable function that gives me that gives me the partial of f with respect to y. You can say partial derivative, or you can just say partial. That gives me the partial with respect to y at any point in the domain, and then I can go through and actually plug in points if I want to. So if I wanted to plug in 0, 0 or something, I could do that here. But right now I just have two functions that represent the partial derivative with respect to x and then the partial derivative with respect to y. So now that we know what partial derivatives are, let's talk about what they mean on a graph. And the nice thing is for you, they still mean exactly the same thing. So remember, back in single variable calculus, the derivative just meant the slope of a function at some point, or a function that gives you the slope of the function. Now, in multivariable calculus, this means the exact same thing, except that maybe we have a function that's like, let's see, it's going to be hard for me to draw, but sometimes we have a function that looks kind of like a slope like this, and then coming through the other way, it's sort of this upward, I don't know if you can even see what I'm talking about here, but imagine like a Pringle, like a chip that looks like a Pringle. So walking along a Pringle in one direction, you're walking like up a hill and then down over the side. So if I were looking right here, if I was kind of at the top of a Pringle chip, I would be looking at a downward facing slope in one direction. But the problem is, if I were then walking the other way on the same Pringle chip and I look up, if I get to that same point, then I would sort of be looking up the hill. So it kind of depends. I don't know if that makes any sense at all. But a Pringle is an example of something called a saddle, like a saddle surface, or it has a saddle point, which just means that in one direction you're sort of going up and over a hill, and in another direction you're sort of going like down to the bottom of a hill and then back up the other side. So it's a weird surface, but it really demonstrates the idea that depending on which direction you're talking about, maybe you're talking about the x direction or the y direction, you could be looking at completely different slopes. So in one direction you could be looking downhill, and then you could turn 90 degrees to the other direction and you're looking uphill, which is kind of a little bit what's going on with this sort of interesting surface. So let's see an example of this one and see how this all works. Now, before we get into this example, notice that none of the axes are labeled in this case. So in this particular example, this is the x-axis pointing toward you. So if you're using your right hand rule right now, remember you have your three fingers, so pointer finger, and then your middle finger sort of points inward toward or like, I guess, across from your palm, and then your thumb sort of like faces up, like a thumbs up. If you're starting your right hand rule here, your pointer finger is going to be facing in this direction. It's almost like your pointer finger is like facing back toward you. And then your middle finger is sort of going off to the side. So this is going to represent the y-axis. And that configuration of your right hand leaves your thumb facing or pointing up, and that is your z-axis in this picture. So we've got x this way, x sort of coming out toward you, y going off to the right, and then z straight up. So we've got our axes configured this way. I'm going to keep them labeled there because it's going to be important. And now let's find our partial derivatives. So I'm going to do a couple things in this example. I'm going to find the slope. I'm going to use my partials to find the slope of the function in the x direction at a certain point. So first of all, just looking at this phrase, find the slope of the surface in the x direction. The slope of the surface in the x direction. Well, remember, the derivative is what finds the slope of a graph. Now, when I say specifically in the x direction, I just mean, well, because there's a y there as well. So what I'm asking you to do is to find the partial derivative of f with respect to x. That's what this means. Find the partial derivative with respect to x. Find the slope of the surface in the x direction. And then I'm going to actually evaluate this at a point, but I'll do that in just a second. So first, let's find the partial with respect to x. Now I'm going to look at this first term. Y is a constant when I'm differentiating with respect to x, so I'm just going to write it and not worry about it too much. And then I differentiate x squared like normal, which differentiates to 2x. And then 5y to the third, well, there's no x variable there, so that just differentiates to 0. And when I simplify this, I just get 2xy for my partial with respect to x. Now, specifically at the point 1, negative 2, so 1, negative 2, I get 2 times 1 times negative 2, and I'm going to get a slope in the x direction of negative 4. Now this is going to be a little bit weird to see on this particular graph, but at the point 1, negative 2, okay, so first of all, let's just get to the point 1, negative 2. I'm going to mark this in a bright green on our graph. So to get to the point 1, negative 2, I need to walk one step over in the x direction and then negative 2 steps in the y direction. So it's like I'm going one step over here and then this way, this way. So you can tell I'm kind of like down below the paper. Like the point 1, negative 2 is sort of down there on this weird slopey surface. Let's clean the rest of that up a little bit if we can. So it's kind of down there on this like sloping surface. We can see there's definite curvature in both directions. I can tell that there's curvature in the x direction because I can see this curve on the function. I can definitely see that in the y direction, so traveling like this way on the y-axis, there's this pretty extreme slope. Now, specifically, we just found a slope of negative 4 in the x direction. So in other words, that means walking in this direction, this x direction, my slope is negative 4, which is a little bit hard to see from this picture, but tells me that from this point, if I'm walking in this direction, I'm walking downhill. I'm walking down a hill if I'm just walking in this direction. So now let's do the same thing for y. Let's find the partial with respect to y, and then in just a second I'll plug in the point 1, negative 2 again. So when I'm finding the partial with respect to y, in this first term, here's the variable, and x squared is just a constant. So this is almost like, you could sort of treat it as like differentiating 5y. If I was differentiating 5y, my answer would just be 5. So it's kind of like whatever's left over in front of the y, which in this case is just x squared. So I've got my x squared answer for my first term, and then my second term is kind of nice. My second term is only one variable, so I don't have to worry about it that much. My second term differentiates to 15y squared. Now, so when I simplify this, of course, it's 16y squared, and when I plug in the point 1, negative 2 into 16y squared, I get 16 times negative 2 squared. Now, let me just look at this really quick. Oh, okay. So in this case, I'm going to get, oh, okay, I got it. I was confused for a second because I was thinking this was going to be negative, and that didn't look like what this picture was supposed to look like. But actually, when you square a negative number, you get a positive. So the slope here is 64, which actually looks exactly like sort of what we were expecting to see, because in the y direction, I can tell that we are walking really, really steeply uphill. So the slope in the y direction is very, very steep uphill, and the slope in the x direction is actually heading downhill. So this is kind of an example of that saddle point, like a Pringle that we were talking about earlier. If you face if you face this direction toward the y-axis, you're looking way up a steep hill. And then if you turn just a little bit, 90 degrees, toward the x-axis, now you're looking down a hill. Not nearly as steep as the y, but still you're looking downhill. So that's how partial derivatives would tell us the slope of a function at any given point. We have to sort of talk about, like, well, which direction are you looking? Because now we have more than one choice. So let's do this again. Now in this case, instead of using the function notation f of x, y, I'm just using z, but it really means the same thing. So I'm finding dz dx, the partial of z with respect to x. So to find dz dx, or I should say partial z, partial x, I just treat, let's see, everything with a y as a constant. Now the problem is here, this second part of my function still has an x in it, and so does the first part. So I really do need to do I really do need to do product rule here. So I'm going to do, let's see, left, and then the derivative of the right. So left d right. Well, the derivative of the right portion of this product is going to be cosine of xy cubed times the derivative of the inside of this function. Well, the y part is a constant, so it's almost like I can treat this as if I'm doing like x times 5. Well, if that were the case, the derivative of x times 5 would just be 5. Well, of course, in this case, it's not a 5. It is a y cubed. So that's sort of our constant for this particular inside function. So that was left d right plus, and now let's do right and leave this one alone, xy cubed, d left. Well, the derivative of x to the fourth is still just 4x to the third. So when I simplify this, let's see, I'm not going to very much, but I'm just going to say x to the fourth, y to the third, cosine of xy cubed, plus 4x cubed sine of xy cubed. So there's our first partial. This is our partial with respect to x. And now let's do the same thing, except let's do partial with respect to z. I'm sorry, partial with respect to y. So dz dy equals, now this is not, it doesn't have a y in it. So we just treat that like a constant, so I have no more need for product rule. I'm just going to keep that at the front because it's just a constant, and differentiate this part. So the derivative of sine of xy cubed is cosine of xy cubed. And now the inside function is a little bit more interesting. The inside function xy cubed, we kind of would treat it as if we're differentiating like 2y cubed. So in other words, you would just kind of write the 2 and then differentiate the y cubed as it is. But in this case, the 2 is the same as an x, so I'm just going to write x times, and then the derivative of y cubed is 3y squared. So when I simplify this whole thing, I get 3 times x to the fifth, because here's one x and then there are the other 4, y squared, cosine of xy cubed. So there's my partial with respect to, with respect to y. So I have both of those. So differentiating with respect to multiple variables is actually, it's actually not that bad, just because you treat the other variable as a constant. Now, things get a little bit more interesting when you're dealing with higher order partial derivatives, because now you can start mixing variables. So let's just start this one. I'll tell you what I mean in a second. Let's start this one by just doing the partial first with respect to x of f of xy. So I'm doing the partial with respect to x. One thing you might want to do now is pause the video and see if you can just find the partial with respect to x yourself. And in this case, the y cubed is a constant, so I'm just going to write that out in front when I'm differentiating with respect to x, and differentiate the x squared like normal, so y cubed times 2x, plus, and then same thing here, the y is a constant, So I'm going to write that there, and then 4x cubed. And when I simplify this, I get 2 xy, y cubed, 2xy cubed, plus 4x cubed y. Now I'm going to do the same thing with respect to y. So the partial with respect to y is going to be x squared, that's just a constant, so I'm just going to write it, times 3y squared, plus, and then x to the fourth, well that's just a constant, but then there's only a y, so that would just differentiate to 1 anyway. So when I simplify this whole thing, I get 3x squared y squared plus x to the fourth. So those are just my first order partials. Now, things get a little bit more interesting when I differentiate again, and notation also gets a little bit weird at this point, but I'm going to keep it as simple as possible. So I'm going to take my first order partial with respect to x, and I'm going to differentiate it with respect to x again. So this is my second order partial derivative both times with respect to x. So now I'm differentiating this that I already found with respect to x. And you can check my answer here, but it is going to be, let's see, 4y and then 3y squared, 3x squared. So when I simplify, 2y cubed plus 12x squared y for my second order partial with respect to x. I'm going to do the same thing again, except I'm going to differentiate my first order partial with respect to y. I'm going to differentiate that with respect to y again. And then I'm going to do something a little bit more interesting. So let's see, 3x squared is just a constant, and then I differentiate the y portion of this. And then x to the fourth, well, that just differentiates to 0 when I'm only differentiating with respect to y. So this becomes 6x squared y. Now, what I haven't talked about is if I can differentiate this first order partial with respect to x with respect to y. And I can. So I can take my first order partial with respect to x and I can differentiate it with respect to y. And that's what I was writing up here because when I said we can combine the variables. So what I'm saying is that we can find the first order differentiated with respect to y, and I can also differentiate this guy with respect to x. So I can mix my variables a little bit here. So let's go through and do this, and we might see something interesting here. So when I differentiate with respect, I'm going to take my first order partial with respect to x, and now go through and differentiate it with respect to y. So I'm taking this guy and differentiating with respect to y. And in that case, the 2x is a constant, and I get 3y squared for the derivative with respect to y, and then 4x cubed for the derivative of the second term. So when I simplify, 6xy squared plus 4x cubed. And now I'm going to go through and do the other way as well. So I'm going to take this guy and differentiate with respect to x. So this first part of the, this first term, I'm going to put the 3y squared is a constant and then differentiate with respect to x. So I'm differentiating this x squared with respect to x, which just gives me 2x. And then differentiating the x to the fourth with respect to x, and that just gives me 4x cubed. So coincidentally, maybe, when I simplify this whole thing, I get 6xy squared plus 4x cubed. And one thing that you probably notice at this point is that these two functions, these two mixed partials, are the same. So I'm just going to note this right now, and then I talked about it a little bit more in the exercises. the fact that these two things are the same will not always happen. So as tempting as it is to say, like, oh, I'm just going to do this once and then say that the other one is the same thing, you unfortunately cannot do that because this will not always happen. It does happen when, let's see, it does happen, I said it in the exercises, it does happen when you have some nice continuity properties going on. I believe it happens when the first order partials are continuous and then also the second order partials are continuous, but I might be, it says it in your exercises, but it won't always happen, so don't just assume, you should check. Now, once we start differentiating, we need to talk about our favorite rule of differentiation, which is called chain rule. So, chain rule would happen when you have these inside functions also being a function of another variable. So like maybe these things are parameterized in terms of t or something like that. And then chain rule uses partial derivatives. So it basically says just first differentiate this whole thing with respect to x and use the regular old chain rule. So when you differentiate with respect to x, you should also then multiply by the derivative of the inside function. So multiply by the derivative of x with respect to t. And then go through and do the same thing again, but with respect to the other variable. So this is actually really, really friendly. You can use the formula to do this, but I'm just going to talk this one out, kind of like we just talked about that. So if I want to find the derivative in this case of z with respect to t, I'm going to first go through and differentiate this whole function with respect to x. Now when I'm finding the partial of this with respect to x, remember y is just a constant, so I only differentiate the x portion of this, which is just 2x, and then y just sort of hangs out there. But remember, x is a function of t, so I would have to multiply by the derivative of x with respect to t, and I'll go ahead and put that in just a second. And then I'm going to go through and do the same thing again, but all with respect to y. So when I'm differentiating with respect to y, the x squared is a constant, and actually the derivative of y is just 1. But when I differentiate with respect to y, and y is actually more complicated, I need to multiply by the inside function, the derivative of the inside function, which is dy dt. So the nice thing is for us, we have these nice functions, x is equal to t squared and y is equal to t cubed, so I can actually simplify this. 2xy times, well, dx dt is just 2t plus x squared, and then, well, dy dt is just 3t squared. So I'm kind of done for dz dt, although I'm actually going to go just a little bit further, because since I already know what x and y are, I'm going to put those things in, because right now I have a function of like 3 variables, and that's sort of ugly. So instead of saying x, I'm actually going to put in this t squared. So 2t squared. Instead of y, I'm actually going to put in the t cubed times 2t plus t squared squared, where this x squared would have been, times 3t squared. So when I simplify all this, I get 4, let's see, I have 2 t's and then 3 more t's and then another t, so this is t to the 6th plus t to the 4th times 3t squared, so 3t to the 6th, and this whole thing simplifies to 7t to the 6th for dz dt. So again, the process is differentiate with respect to x, and then just don't forget to multiply by the derivative of the inside function, and then do the same thing for y. Differentiate the whole function with respect to y, and then go back and multiply by the derivative of the inside function. So chain rule in multiple variables just says find your 2 derivatives and then add them together, and just don't forget to multiply by the derivative of the inside function, just like we normally do with chain rule. Now at this point, you are prepared to do problems, let's see, you can do 4, 5, 6 is another one with partials. So again, kind of using different notation, but the partial of z with respect to x and the partial of z with respect to y. And same thing on number 7, using that same notation. Now, number 8 is an interesting problem. This is all using partial derivatives. So when it says instantaneous rate of change, that's definitely a derivative. And it actually says even with respect to s, if d is held constant, what that's asking you for is the derivative of v with respect to s. It's just a partial derivative. So you can do number 8 even though it's a little bit different than the wording on the previous problems. And then numbers 10 and 11 are very similar to what we were just doing. So now you're just using that chain rule process. So in this case, you're going to have dz dt, again using the same formula. So go through and differentiate everything with respect to x, but don't forget, multiply by the derivative of the inside, and then do the same thing with respect to y, and don't forget to multiply by the derivative of the inside. Now, you can probably imagine how you would extend this formula if there were more variables, because you'll notice it's kind of the same thing over and over again. So when it's saying use a 3-variable version of the chain rule, I'm not asking you to do anything crazy. You just put a dz, or actually in this case it's going to be dw dz. Just put a third term here and then do exactly the same thing on number 11. So you're prepared to do those problems now, or you can go on and watch the next video.